Hi, Eric Rexted, continuing our discussion about analysis of distance sampling data. We've gotten to the point where we are trying to fit models to our perpendicular distance data. Soon after we begin to fit models to data, we want to be able to characterize that fit. We want to know if we're doing an adequate job. So I'm going to spend a slide looking at the tool called likelihood that does the job of fitting models to data. And then something called Akaike's information criterion that we can use for a relative assessment of fit. We can use it to contrast a suite of models. But in addition to that, we also want to be able to do an exact or an absolute measure of fit to determine whether the model that we have produced is an adequate description of our data. So what's likelihood? Likelihood is going to be used in conjunction with our probability density function, f of x, which was defined as this probability that an animal is in some distance from the transect line between x and x plus dx. That conditional probability, given that it was detected somewhere between the transect line and our truncation distance w. When we record exact distances in the field, those exact perpendicular distances, then this is the likelihood that arises from those data, where these little x's are the data that we collect, the perpendicular distances from the transect line. So the process then becomes one of identifying, estimating parameters in our probability density function f of x such that the value of this product of all of these probability density functions, known as the likelihood, is maximized. So we either maximize L itself, or more commonly we maximize the log to the base e of the likelihood, in which these products, here, 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 and everywhere else, turn into sums. So that is the machinery underlying the distance software, where it looks at the data that you've provided to it, tries to come up with parameters associated with the detection functions that you've asked to be fitted, and tries to produce the best estimates of the parameters of those detection functions that maximize this likelihood term L. I raise the issue of likelihood here because we're going to use components of that likelihood to try to assess the relative fits of the various models that to which we subject our data. So this brings us on to Akaike's information criterion, in which, lo and behold, there's our likelihood value appearing. This time is a log. And so our Akaike's information criteria has two components to it. It's the doubling of the log likelihood, to which is added double the number of parameters in our model. This makes a very simple device that we can use to try to decide what model is most appropriate for the data that we've collected. There are some nice properties here. We don't have to have the models living inside one another, nested within one another. The criterion that we use to decide what our most appropriate model for our data is to use the model that has the smallest AIC. And that gives us a relative measure of fit. This AIC harks back to an earlier comment I made about trying to find the best compromise between bias and precision. And I noted that bias was going to decrease as the number of parameters in our model went up, but that our precision or our variance was going to deteriorate as the number of parameters increased. And so this is where the two components of AIC comes in. This term is a measure, an assessment of how good our model fits our data. And so this term improves as we increase the number of parameters. However, this term also blows up as we increase the number of parameters. And so it's the trade-off of bias and precision that are represented in the two quantities of the AIC. There's been a lot written about AIC. You can consult either the distance sampling books by Buckland et al. Or a variety of other places in the literature to learn more. So we'd like to be able to use AIC to give us an opportunity to select or choose among competing models that we have fitted to our data. And that works very well under many circumstances. However, there are some circumstances in which AIC cannot be used to arbitrate between competing models. We can't use it, for example, when we employ truncation. When we employ truncation, the number of data points in our samples change. And so a model where we truncate 10% of our data contrasted with a model where we truncate 25% of our data, the sample sizes differ, and because the sample sizes differ, we can't use AIC to say which is the preferable truncation distance, because we change our data, we change our sample when we change our truncation. Likewise, if we have grouped data and we move the cut points or the locations of the bins around, that fundamentally changes the data. And once we fundamentally change the data, we can no longer use AIC to ask where are the best places for cut points. Likewise, as a corollary, you can't use AIC to say, oh, I have exact data, but I can bin those data at analysis time and try to determine whether I should or should not bin my data for analysis. AIC is of no use in trying to help you make that determination because the data, the sample sizes will differ in these two instances, and hence AIC can't arbitrate between them. So that's what AIC does. It helps us to select between models with a few caveats in terms of when that's inappropriate. So AIC gives us this relative measure of model performance. Models relative to one another, we can assess their performance. So AIC is useful under most circumstances for model selection. Once we have chosen a model, or perhaps a couple of candidate models on the basis of AIC, we have a further level of scrutiny that we want to perform. Namely, we want to come up with an absolute measure of fit of our models to data. And so goodness fit gives us exact measures of fit, either in the form of chi-square tests. Chi-square tests I'll talk about in a second. they help us measure the disparity between what we've observed in our data in terms of distribution of perpendicular distances and what our model would predict should be that distribution of perpendicular distances. So a chi-square test is one way of doing that, and something called QQ plots and test metrics that come from QQ plots when we have exact data. Both of those methods are available to us for measuring absolute goodness of fit. I'll start with the chi-square tests because you've seen chi-square tests in the past in your brief forays with statistical analyses. Goodness of fit tests measure the difference between observed and expected frequencies. And so when we have our perpendicular distance data, we have the number of sightings that we had in bin number 1, and we compare that against the number of sightings our model predicts ought to be in bin 1. Squares that difference and sums all of those differences across all possible bins. And the distribution of that test statistic is assumed to be chi-square. Okay. So all of our data, all of our n sightings, are distributed across these U number of bins. Where does this pi hat come from? This pi hat comes from the model that we have fitted, our estimated probability density function. And so we look at the proportion of the area of our fitted probability density function in each one of these U distance intervals and use that to compute our expected number of sightings in each of the bins. We can then perform a hypothesis test to say, is our fitted model an appropriate representation of our observed data by contrasting the calculated test statistic as opposed to the critical value of this test statistic. Let me show you how this works. Here are some line transect data on a forest bird collected by Professor Buckland. We have the usual histogram that we've seen in the past and the fitted half-normal detection function to these line transect data. We can see there are some discrepancies in various places between what the model predicts should be the number of sightings and the actual number of sightings. So the question asked by the chi-square test is, are those departures, when we look at them across all of our data, are those departures between the observed values and the expected values sufficiently large that we think this model isn't adequate for the data? So a table of observed values and expected values can be computed across all U of these different cut points. And so this says, how many detections were there between 0 and 12.5 meters? Professor Buckland had 16 sightings of this bird species in that distance category. The model predicted that there should be 15.3 detections in that bin. So we can calculate the chi-square value for that particular bin by taking this difference, squaring that difference, and dividing it by this expected value, turning out to have a very small chi-square value because the discrepancy there is small. Discrepancy here is small. Discrepancy here is small. Summing up all of those chi-square values, we come to a value such as 4.7 with 6 degrees of freedom. The probability that that value arose by is a good depiction of our data is pretty high. So our null hypothesis is that this model fits our data. With this p-value, we lack the evidence to reject that conjecture. And so this value, this large value of p, suggests that this model is an accurate, adequate depiction of these data. That's how a chi-square test works in trying to assess absolute fit. Now let's move on to the idea of these QQ plots. So here again I have an example in which I have a histogram with 9 detections, 6 detections, and 3 detections in the 3 bins, and something that approximates a fitted detection function through those data. Okay. When my distances are exact, I know exactly where in the interval between 0 and 1 those 9 detections fell. Notice there were 4 of them very close to the line, 4 more of them sort of scattered out across the middle of that interval, and 1 of them right on the boundary between 0 and 1. Okay, so there's more information about where those sightings were made that is essentially lost when it simply says there were 9 sightings in the interval between 0 and 1. So can we use that more refined information to come up with an enhanced estimate of the adequacy of the fit of our model to our data? The way we go about doing that is recognizing the rate or the speed with which we move through our data cumulatively. So half of our data lived between 0 and 1. 5/6 of our data lived between 0 and 2. And 100% of our data lived between 0 and 3. Here's a quick animation to show you how we assess fit using this thing called a QQ plot to contrast the rate at which we move through our observed data, depicted here on the x-axis, compared to the rate at which we move through our expected probability density function. We can contrast that looking only at the 3 points associated with our histogram at distance 1, distance 2, and distance 3 to state we moved halfway through our data between 0 and 1, 5/6 of the way through our data between 0 and 2, and 100% of the way through our data between 0 and 3. But more finely, we can also look to see at the spacing within those bins to find out if the speed with which we're moving through our data is equivalent to the speed with which we were moving through our predicted probability density function. When the speed of those 2 things is equivalent, then the points on this QQ plot will fall along the 45-degree line. And so the QQ plot is, our expectation is when we have a model that fits our data, these points of pace through data and pace through prediction are going to be equivalent, and therefore the points will land on the 45-degree line. So that is an example of when we have good model fit, our points live on this 45-degree line. And it's a contrast of the rate at which we're moving through empirical means coming from data, as opposed to the rate at which we're moving through the fitted cumulative distribution function. Fitted as in coming from our model. So that's when we have good fit. What does the world look like when we have poor fit? Notice, I've now taken 8 of those 9 data points that used to live in this interval, and I've piled them all up onto 0. So I have really poor data because this observer rounded all of the distances measurements made between 0 and 1 and said, oh, they must all be 0. Now, notice when we do a chi-square test, this chi-square test doesn't resolve that those distances are all at 0. It simply says, well, they're somewhere between 0 and 1. And so the height of this histogram is still 9, as is this one 6 and this one 3. Okay? So we still have half of the area under the histogram living in this first bar, 5/6 living in the second bar. So if we performed a chi-square test on these data, we would not pick up this pathology because it would be hidden from us when we've aggregated the data into, well, how many data points were there between 0 and 1? Now then, let's try to look at what these data, how these data would appear if we made a QQ plot of them. Well, there are these 3 mileposts for our data. Half lived in that first interval, 5/6 in the first 2 intervals, and 100% in the first 3 intervals. So in those 3 instances, our point would land on the 45-degree line where it belongs. However, this animation shows that because all of these 8 data points were at distance 0, we moved nearly halfway through our observed data before we moved off of the x-axis with our fitted model, because our fitted model said, well, at distance 0 on the transect line, there's actually only a small amount of mass of our PDF. And so this region of the QQ plot says, oh, look, there's a disparity or a discrepancy between observed values, all heaped at 0, and predicted values that says we're moving gently away from our peak detectability at distance 0. So this is what we would see if we had a QQ plot in which we had a poor fit demonstrated as a result of heaping at distance 0. So this is what we would see if we looked on a distance printout of poor data. So these red dots indicate that there's a discrepancy between data living on this 45-degree line. The question is, how big is that discrepancy? Our QQ plots don't give us a number. It doesn't quantify the fit to say that fit is really bad or extra bad or utterly bad or horribly bad. It simply gives us a picture. That's what a QQ plot does. It's a plot. It's a picture. So, to aid in the interpretation of the pictures, we can quantify those pictures using a couple of different types of statistical tests. The first one is given the name the Kolmogorov-Smirnov test, and it looks at this QQ plot and asks, where is the discrepancy of the red dots from the 45-degree line, where they belong, if there's a good fit of our model? How big is that biggest discrepancy? And the Kolmogorov-Smirnov test will then tabulate how big that difference is to convert it into a test statistic that says the probability that we would get a discrepancy that large if our model was correct is some p-value. So the Kolmogorov-Smirnov test uses the biggest difference in the QQ plot to convert the visual image of the QQ plot into a test statistic with an associated p-value. The test still being the same as with the chi-square test, namely the hypothesis that being that our model fits the data. Cramér-von Mises test does much the same thing. It looks at the QQ plot and transforms the location of those points into a test statistic that allows us to assess the veracity of the hypothesis that the model fits the data. In this case, rather than just looking at the biggest discrepancy, it looks at the squared distances. So looking at, there are no discrepancies up here, and these discrepancies all get squared, summed, and then squared and then summed. In addition to that, the Cramér-von Mises test, given that it computes deviation for each dot, it can weigh those deviations differently to say it's very important that these discrepancies be as small as possible. And so it can say any discrepancy at small distances from the transect can be magnified to say this is bad fit, because it's much more important that the fit be good close to the transect line than at great distances away from the transect line, because we're mainly interested in producing a good estimate of what that probability density function f looks like when it's evaluated at distance 0. So here are some real data. This goes back to Professor Buckland's Chaffinch data, for which I showed you the chi-square goodness of fit test. Here's what the QQ plot looks like for those same data. And you'll notice a slight discrepancy. And that discrepancy in the form of stair steps here is consistent with the idea that there may have been some rounding in the perpendicular distances that Professor Buckland recorded. So rather than all of these red data points landing on the blue 45-degree line, we see a number of data points living on this horizontal band, then a jump, then another horizontal band, then a jump, and another horizontal band. So that's an indication of some departure from or deviation between our observed data, empirical, and our predicted or fitted cumulative distribution function. So we can see there is some lack of fit. That lack of fit seems to be most pronounced in this area, and it gets less pronounced as we get farther away. The question then becomes, is that discrepancy sufficiently large for us to cast doubt upon the hypothesis that this particular detection function model fitted these data. So program distance computes both the Kolmogorov-Smirnov test and an associated p-value that suggests there's very little evidence to suggest this model is inadequate. It also computes the Cramér-von Mises test, and it computes that test in two forms. One in which each data point receives equal weighting, and a second variant in which there's greater weighting for the data points at small distances from the transect and less weighting for data points at large distances from the transect. In all three instances, we have little evidence to suggest that our model is not consistent with the data that we collected. In other words, the model that we fitted to these data is adequate. And that's confirmed not only in the chi-squared tests, and the chi-square test requires us to take exact data and convert it to binned data. So there are some judgments that we, the investigator, have to make with regard to where those cut points ought to be. The Kolmogorov-Smirnov test and the Cramér-von Mises test relieves us of the necessity of inducing those subjective cut points. So when we have exact distance data, it's best to use either the KS or the CVM test because it removes one level of subjectivity in the analysis of goodness of fit. So these QQ plots show us visually where there is discrepancy between what the model predicts and what we've observed. They do not require us, the QQ plots do not require us to come up with those cut points. The visual image of the QQ plots can be converted into hypothesis tests, testing the goodness of fit of our models in either the Kolmogorov-Smirnov or the Cramér-von Mises variants. And finally, that Cramér-von Mises variant has the opportunity for us to give higher weight to fit near the transect line, which is critical to our ability to make reliable estimates of abundance or density.